Not quite the same thing, really. Not quite. That's when you need PR, not public affairs. And PR and public affairs come together when it comes to policy and public relations. Okay, that's what Jamie and I do. Omnicom is, if you haven't heard of them, a massive US-owned advertising and marketing business, and they own two companies that Jamie and I work for. FleishmanHillard, which is a PR business, and I'm the head of digital reputation in EMEA, and my background is journalism, digital marketing. And Jamie?
Thank you very much. Morning, everybody. I'm a strategic communications consultant, and what that means is that I work with leadership teams, I work with boards to really put in place the right strategies, communication strategies, engagement strategies to help them work with their most important audiences that really stand to influence their prospects for growth, their market position, and their license to operate. And so really we are focused on the business of reputation.
Yeah. So why are we here today to talk about reputation management? I know it's not necessarily something you all care about day to day, but the whole point is we're talking to audiences like you about the implication of new technology into automation and automatic processes. Because if you continue on the road that we're going on at the moment, those agentic processes could lead to crises and reputational crises as well. And that's our background. So we're here really to get you prepared for what's coming. So whether it's AI agentic processes or whether it's quantum, there will be trouble down the road, and we're here to prepare you for that. We've both got backgrounds managing crises and reputation management for huge multinationals. So this hopefully will be useful to you to be able to go back to your businesses, go back to your colleagues and talk to them about some of the things that may be coming down the road. So we got some questions for you initially. So if we just skip forward, Jamie, next slide. So I bet you we get some good answers to this. Who's used AI today? Hands up, please. Good. I'm glad to see it's most of you. Okay, tall man I happen to know is Tim. What did you use it for today? What did you use AI for? What did you use it for this morning, you specifically? Go-to-market materials. Did you put any information into the system? So, safe. Anyone else stuck their hand up and used it this morning? Want to tell me what they used it for? Yep, what did you use it for, Frank? Personal assistant, great. So two pretty good uses in the back, yeah. Well, there we go. That's a great example. So we've got a business use, a planning use, editorial planning use, and a personal use. So there's three very different uses. All of them have possible issues with them if you upload personal information to the system and it's not secure. So the next question is, Jamie.
Who inputted personal data into a non-secure model this morning?
Did anybody do that? Did anyone want to own up to doing that this morning?
You're among friends here. No
Not this morning.
Here. Any information that you wouldn't ordinarily like to be shared outside a safe or secure environment?
Okay. Good. Well, we've got the right room. I can assure you, in our colleagues' circles, almost 99% of people would stick their hands up and say yes. Yes. So you guys obviously know the risks. Do you, madam at the back? Yeah. Well, GDPR does it quite well. Anything that can be used to identify you. So that's generally what is considered to be personal data. So anything that's personally identifiable, it identifies, the machine can identify you from it against other people. That's the way GDPR defines personal data. Next question is, this is an interesting one. So this is down to reputation management now. Who has checked a popular LLM to see what it says about their C-suite and or their business? Yep, stick your hand up. Yeah, and did it give the answer you wanted? You, sir. Did it give you the answer you wanted? Pretty happy with it? Anyone else stuck their hand up? Give you the answer you wanted? No. What was the issue? Can't imagine who'd do that.
That's encouraging.
Yes. So the point of this last question is that reputation starts with AI. It starts with AI because AI will have a view on you as an individual and or a business. Okay, that's what it's designed to do. It's designed to give you an answer. A large language model is designed to give you an answer. So this is going to impact the reputation of your C-suite and are your business unless you do something about it. So, and that's what we're going to get into now. So as we get into our slides, I want you to think about the answer to that last question. Right, let's go to the next slide. Jamie.
Well, and so the starting point of all this really is, of course, that most of the discussions that take place in boardrooms or among procurement committees in all different in sectors and so both in private and the public sector too, around AI and quantum really are focusing on capability, speed, efficiency, competitive edge. And all these conversations are valid and important, but they are incomplete because every technology creates a corresponding reputational liability. And so the question for everyone in this room and your leadership teams back in the office is not whether that liability exists. It's actually whether your ability to react to those problems has kept pace with the speed at which you've evolved your technology stack. And so in high stakes environments, in government procurement, in critical infrastructure, in defense and financial services, capability is actually rarely the sole deciding factor as to who wins and who loses. The reality is that trust is often as important, or in some cases, even more important. So the strength of your technology might get you through the door, but actually your license to operate is harder to win and even harder to maintain. So this is particularly true in a world where people are more able and more willing than ever before to be public or to make public their perspectives and hold companies to account about their conduct. So remember, everyone with a social media account can serve as a journalist, can serve as an activist, a supporter, or a detractor. And so it's really important to keep these factors in mind when you're developing new technologies and thinking about how you roll them out.
Okay, let's move on to the next one. So, I mean, this is designed to sound scary, guys. I mean, some of the data I've got on the right-hand side is designed to actually hold your feet to the fire and make you realize, and I should have actually withheld one of these pieces of information. So actually, without looking at the last bit of data on the screen, do not look, look at me, look at me. How many of you trust agentic systems? Stick your hands in the air. Okay, well, actually, you represent probably the UK public then, because the figure on the screen says only 14% of UK consumers are comfortable with fully autonomous systems. Only 14%, and yet that is what we're talking about here today. That's what we're talking about: agentic systems that automate business processes. But only 14% of consumers are happy. There's a massive lag then between the technology and the trust, and that's exactly what Jamie said. But also deep fakes, guys. So you will all know that large language models and generative AI enables fake video, fake imagery incredibly easy. Like 4 or 5 years ago, it would have taken a team of creatives to do that in my business. Nowadays, it just takes one prompt, right? You can get a fake video in seconds. Last time I spoke here, I think I actually created a video within seconds as well and demonstrated it, or at least I thought I was going to do it and maybe didn't do it. But it is very, very possible to fake an image or fake a video very quickly. And in doing so, a nefarious actor can put online something that could damage your business in seconds, because it could either be your CEO saying something you don't want them to say, or it could be someone talking about your business in a way that you don't want them to. And this disinformation, this fake news, statistically travels way faster than real stuff. So whenever you've got that fake information in the realm, you will notice how quickly it follows on social media, how quickly it then booms on social media. The fake stuff travels faster. So you want to think about this sort of information whilst you're talking and thinking about now your agentic systems. What happens if the fake stuff gets out there about you or your business? Have you got a plan? Back to you, Jamie. Oh, it's me, sorry, apologies. Didn't have a plan. So this didn't, it would have done it for me, wouldn't it? Yeah. So look, in the old days, guys, what we used to do is talk about transparency, the black box issue. How did it work? What was it? How did it build? How did it create stuff? No one really understood. So the process problem in the old days, when I'm talking about the old days, I'm talking about 2 or 3 years ago, when we're talking about ChatGPT 3.5, ChatGPT 4. No one knew how it worked, right? We still don't know how it works. But the way organizations planned and governed it was about putting through governance processes that enabled employees to think about what they were doing, because an employee would be the one who prompted the system. So if you put a proper secure governance process in place, you weren't getting dangerous output. Now think about what's happening. The autonomous systems are starting to come into the system, and the real decisions are not being made by humans, they're being made by machines. What does that mean? That means that failure is potentially public, because when a system is operating autonomously, it could create something in the public domain that you wouldn't want it to. So your failures are now potentially public. So in the old days, what we talk about is governance strategy. And within 2 or 3 years now, we are saying that every organization who is talking about agentic AI should be thinking about a communications plan, because it will go wrong. Jamie.
And where it can go wrong really can be categorized in these 3 quite broad pillars, really. And so this actually gives you almost a structure straight away for how you think about how you prepare yourself to stand up your solutions to those who may have a perspective on that. And I think it's important to remember that when you're dealing with broad sets of audiences, and even those with whom you're going to be engaging directly, remember that sometimes a little knowledge is a dangerous thing. And so you are the experts in the room. It's really important to work on the assumption that the people you're engaging don't necessarily share that level of technical know-how. So these are 3 areas of really kind of inherent reputational risk. And I want to put those in the context of the world that our stakeholders really are actually living in, because these technical risks don't exist in a vacuum. They actually land in a public environment that is becoming measurably more hostile to some of the technologies that are being rolled out and the speed at which they're being rolled out too. Remember, the public, when they look at pieces of technology, will inherently ask, what's in it for me? They will look at it through that lens. We've already talked about some examples, relating to medical records. I won't dwell on that further, but you sort of see what I mean when you put it in that sort of context. A headline number from some really interesting research, which I'm sure some of you will have seen already, from Pew earlier this year, came up with quite a startling fact that half of American adults say that AI makes them more concerned than excited. And in a room full of people who are really excited by that, that's just something that's worth remembering. The concerns that they have are distinct. Some of those will be well rehearsed, but they really kind of revolve around a couple of different categories: jobs, misinformation, privacy and security, and increasingly the environmental cost as well. Because of course, as we've seen in the United States in particular, the rollout of data center infrastructure is causing huge amounts of local and planning controversy as well. 71% of Americans are opposed to data centers being built in their local area, and Morgan Stanley recently described that dynamic, that community opposition, as a binding constraint, not a planning constraint, but a binding one as well. And so here's the thing that maybe should give us all a little bit of pause in the room. Most of us, as I said, are really excited about this technology. We see the potential of it hugely. But actually our proximity to the technology can sometimes obstruct how a broader set of audiences really perceive that technology to be. And so if you think about 39% of AI experts think that AI adoption will bring about fewer jobs. Comparatively speaking, 64% of the public think that that's a real risk. So it's a 25-point perception gap between the people building the technology and the people who are going to be living with it and using it. And so some of these technologies are being approached with real hesitation and not a huge amount of trust. So that's fundamentally different between the technology and its users that most of us have seen before. So if you think about these three key pillars, that actually starts to be quite instructive in the way that people are going to think about this. So with that, let's dive into these in a bit more detail.
I'll just give you a little bit more detail on these 3 pillars, guys. So if we skip forward, Jamie, to so accountability without humans, okay? What does that really mean? In the old days, when I sent an email, I was accountable for the email. Anything in that email was from me, and I'd happily sort of stand up and say, if it's wrong, it's my fault. I talk to my team in my business now, and most of that's based in Brussels because we do a lot of public affairs. I say, it's up to you to press the send button. So everything before the send button could be done with a machine, but it's up to you to press the send button. That's not agentic. That's a human in the loop pressing the send button, or publishing the article, or getting in touch with the media. All of this is potentially done agentically, as in autonomously. Now, when a system is autonomous, who's culpable? It's not the person behind the system just watching the green lights go. It's the person who built the system. And that potentially in this room is all of you guys, right? So you guys could be liable for failure. And that's what I want you to think about at the moment. So when the procurement systems start to operate, when government stakeholders start to get round a table to discuss your solution, they'll be thinking, not is it capable, but can I trust the people behind it? And that's what this is all about. Second slide. Second flashpoint. Okay, so trust is outsourced. We talked about outsourcing trust to AI. When any of you want to understand a new business or business partner today, you're going to get into Google or ChatGPT or Claude or whatever it is, you're going to ask a question about them. You're not asking a partner or a colleague, you're asking an LLM to find out about somebody. So trust is already being outsourced to AI. If you find a story in that that's juicy, in that answer, that's a good story. That's a narrative I can run with. So you don't actually look for the facts, you'll follow the story. If that person you want to do business with, if it says something saucy about them over here, I guarantee you'll read it. You're not going to check the facts. You're going to read it first, then you'll check the facts. Did you have time? Maybe you didn't. Critics don't need understanding. So the media doesn't need to verify everything they publish as long as it gets clicks. They'll stand it up later. This is this idea that nowadays good stories have to be published quickly, because if you don't get clicks. Anyone a cricket fan in this room? Yeah. Did anyone see what happened about Ben Stokes yesterday? Yeah, that was published within seconds. Within seconds. Is it all true? We don't know yet. Doesn't matter. You know, the media wanted to be first published. Ben Stokes, by the way, England cricket captain, caught in a nightclub having a fight again, right? The point is that was published within seconds. Probably 10 years ago, that would have been 24-hour delay at least. Yeah. So that the media would have stood up the story and made check the facts. This is happening quicker and quicker. These crises now perpetuate far faster. And this distrust, now, this is to the cricket analogy, do we trust Ben Stokes? Do we trust the English cricket team? That's the problem now we've got. Back to you.
The other thing I would add to this is that I ran through the exercise that Pete outlined right at the beginning. You look at a large language model for information about your own business. I ran this exercise just anecdotally with a client fairly recently and just asked for a corporate profile of the business across 4 different large language models. And all of them came back with something different. And so some of it was current, some of it was really historic, some of it was so prehistoric almost that it actually really didn't bear much resemblance to the business as it was today. So again, actually pointing all of these tools towards a source of truth is incredibly important, particularly because, and also, your customers are going to be receiving that information as well.
I'm going to fly through because we're running out of time, Jamie. So
yes,
the flashpoint 3 is the end of secure by default. So what happens when these systems start to operate on their own? Effectively, it's now an assumption. I've already gone over this, but essentially stakeholders expect the resilience, and crisis prevention planning is not nice to have now. It's a must have, because the systems will at some point, as they embed, start to fail. So are you secure? In the age of quantum, I know some quantum experts in the room, cyber data and security of cyber data is a big question now. When it leaks, what are you going to do about it? Let's go to the next slide, though. Okay, this is all about what I call the reputation waterfall. I won't go into it in great detail, but it eventually summarizes a scenario where everything starts going badly in a sequence. Okay, and it could repeat itself. Stages 3, 4, 5, and 6 can easily repeat themselves. And this can happen. This, 10 years ago, without AI, this sort of reputational waterfall would take days, weeks to happen. This can now happen in seconds. So, AI systems learning from distorted data is actually happening now. Go to the next one, Jamie.
And let's not discount human nature in the way that we plan for these things, because actually it's something that you need to really anticipate and preempt when you are in the design phase of your solution, because it's far easier and far cheaper to do it that way rather than to try and have to deal with a problem after it's happened. And so actually getting that narrative right, anticipating the needs of those audiences right at the start is going to save you a huge amount of time and potentially a huge amount of reputational cost as well.
So we've sped it up really quickly. If you go to the next slide, these are the 5 things that you should take away from this presentation, other than hopefully some of the things we've said. But if you had to do something now for your business, stress test your reputation via AI. That is you going into AI systems and asking, what does it think of you? What does it think of your people? What does it think of your C-suite? What does it think of your business partners, your procurement systems? I know procurement's another theme we're going to talk about today. But does AI have a view? Because it's bound to have a view. It's paid to have a view. It's built to have a view. What is that view of you and your systems? Decide what AI should know about you. That's not the same as number one. So once you found out what it knows about you, what it thinks it knows about you, decide what you want it to think about you. Okay, that's not the same thing as what you've just discovered. Put your human side front and center. That's crucial. So that's the people in the room. Jamie just talked about the importance of humans at the beginning of the system. But when it comes to managing a reputation, don't put forward a press release nowadays. Put forward a person that means something. Get your people, your C-suite, in front of video, in front of cameras, in front of the media, on social media, so that the systems, the AI systems, know what the humans in your business look like, sound like, and behave like, because they therefore can't be impersonated that easily. Number three is crucial. Also builds trust, number three as well. Build AI into crisis readiness. That essentially means how quickly can you start up your crisis communication plan. Jamie's an expert on that. Grab him if you want to talk to him. And then treat governance as reputational capital. So you need a governance plan. And when you have a governance plan, you tell everyone what it is. In the old days, it was we put it under the pillow, we hide it, we get it out when we need it. Nowadays, a governance plan is part of your reputational management plan. It's crucial. How does the system work? Where's the human in the loop? Publish all of that. Because if you don't display that, when the shit hits the fan, people can ask you those questions. Okay. We sped through that, guys, because I got a little look from Corke saying, get on with it. So this is us, Jamie and me. We both work for Omnicom, different parts. Jamie, Mercury, US, bringing US products and US needs and businesses into the UK. I'm more EMEA, so I'm generally Brussels-based, and I deal with EU policy and what it means to businesses in the UK and in Europe as well. So we've got our emails on the bottom. If you want to ask any questions about anything you've just heard in the last 15, 20 minutes, we're here. Otherwise, you can catch us afterwards.
Brilliant. Thanks ever so much, guys. That was superb. Thank you. Peter, are you going to be hanging around? I was going to say if we could do it at lunch, just because we are about 10 minutes behind and I want to get Nicola up. But Jamie, you're about to go and catch a flight, right? So Jamie won't be here, but Peter will be around at lunchtime if anyone wants to have some questions. Thanks very much, guys. Next up, we have Nicola. Are you? Ah, there you are. Nicola from King's College. She's going to talk to us about, it's here. I've got you. Which problems are quantum problems? Back? Yes. So.
If I miss it, go back.
Okay. Thank you very much.
Right. Thank you for letting me come and present today. My name is Nicola Jane Buttigieg, and I am currently doing a PhD at King's College London, and I also work for the King's Institute for Artificial Intelligence. So my PhD is on the transition from classical to quantum machine learning. So for people who are currently classical machine learning engineers working with classical data and how they can transition to understand how to run these algorithms on a quantum machine, if they will even run on a quantum machine, and if the problem is actually a quantum problem or a problem that can warrant using a quantum algorithm. So I might start with, oh, I didn't know this slide was here. Oh. There's my biography. I probably should have had that while I was speaking. Okay, so what I've done is I've considered the scenario for today, and I'm not dealing with a quantum conference. What we're dealing with is what can a quantum machine do with everyday classical data? And that is a very specific thing. It's called a hybrid quantum algorithm. So what I've done is I've considered what we don't do doesn't get done. So we talk about it, we see comments on LinkedIn, possibly people have generated these things on AI or they've twisted someone else's post. There's this buzz about quantum. What does it do? It's a machine that works really quickly. It's a really strong computer. Yes and no. So what I might do is I might give you some case studies so you can actually see what a quantum machine can do with classical data. And then in explaining that, perhaps we can then see what is a quantum problem with quantum data, and then, a classical data problem using a quantum algorithm. Because when I came here to IBM a few weeks ago, we had this annual event with all these, writers of algorithms. And I was blown away because this very board was like this, with all the possibilities for quantum. And my area, which is hybrid quantum machine learning with classical data, it was like over here in a tiny little bubble. And I remember thinking that is so tiny in the scheme of things. But then I spoke to Sam, who was managing it that day, managing the event, and he said, yes, but it's a very interesting area that people are looking at. So yes, it's small, but potentially it's the window to everything else. Because until people can start using classical data with a quantum algorithm, they can't start to understand how these quantum machines work. So I've been using time series data for using NASA data from the satellites, different kinds of NASA data. I've been trying it with artwork, with mosaics. Been trying a bit of fintech and learning about the stock market. Now there's an interesting area that I never thought that I'd be exploring, but there you go. And of course, my best friend, Qiskit. So when I jumped into this whole situation as a classical machine learning engineer, I tried Black Opal. I tried, there's lots of different, there's Penny Lane, there's different, what are called programming languages, syntax, but Qiskit has some visualizations, and it's also got a training badge, which was golden for me. So then I started to ground what I was trying to do with my projects in these examples that this Qiskit machine learning badge had. So I highly recommend it if it's an area that you or your team are looking into. And then down the bottom, we got GPKit. Now that was written by an astronaut back when he was at MIT. He's moved on to a more enhanced version of it now. What it does is it optimizes engineering, and you can use it in conjunction with Qiskit. So I've been trying a few different things. I'm still a student, but I thought this might be the best way to try and explain what we can. Sorry, I'm trying to make this thing click. There we go. A little bit about me. I think I've already said enough about myself. I probably should have had this slide up earlier. But what I do want to point out is on the 17th of June, the first out of my 5 projects today, I am going to run a workshop, and it is in fact on limit order books. So if you are in fintech and you have a machine learning engineer, a normal classical machine engineer in your team who is interested in what quantum machines can do, I'm actually going to pull apart that project and show you how it works in Qiskit, and I'm going to base it on that quantum machine learning badge so that you can then maybe look at taking this credential, having seen it actually work in a project. And the topic is fintech, but I have actually got use cases for 5 different projects today. Oops, this. Hang on, Qiskit. Okay, so first of all, this is a quantum machine. You've probably seen one downstairs. So we hear superconductors, what do we hear? Lasers, all these terms. So what is a quantum problem? Well, let's try and break it down. I know this is not a technical talk, but let's try and break it down so that you can understand what these use cases are benefiting from. So complexity beyond classical scaling. Okay, most simple thing to describe, brute force, with passwords. Every time you make something longer, the more combinations there is to try and brute force, right? So it grows exponentially, to put it very simply. Hilbert space mapping. Okay, what is a Hilbert space? Okay, let's talk about 2D plots. Let's talk about Euclidean space, high school mathematics. So let's pretend you've got data points, and there's red ones here and blue ones here, and you can draw a line through them to classify them, right? They're linearly separable. Now, what happens if you've got data where there is a blue circle of dots around like that, and the red ones are all in the middle? How on earth do you cut a line through that, right? Now, if you imagine that square plot, we make it 3D, so they're floating, and you've got the red ones up here and the blue ones underneath, you can actually slice your hand through the middle and separate them that way. That's 3D. Now, Hilbert space, we're talking 1000D, right? You can't visualize it, but that's what your quantum machine is dealing with. Okay, non-linear dynamics. So essentially, instead of having a straight line, if you imagine inside this Hilbert space, the lines are kind of going all like this to try and separate them, right? But if you could visualize it, to the quantum machine, that is flat, right? It's making a straight line. We as humans would think it's all squiggly. The quantum machine thinks it's flat, right? And then what is quantum advantage? Okay, so the fact that we have this Hilbert space means we have this advantage whereby we can separate these data points in this massive, massive space. And it gets even more interesting. So normally, your data points will represent one thing. So I've got a use case with an aircraft coming up, and we're actually using GPKit to optimize the aircraft. And the way GPKit works, it's all the forces and constraints on the plane to do with the weather, you know, wind pressure and so forth, so the wings don't snap. And also the weight. So we've got lift and drag. Now, if you imagine the NASA data we're using, humidity, temperature, these are singular numbers, right? Singular data points. But what happens is, in a quantum machine, these data points sort of get fused together as one entity, and they become entangled, right? So your normal machine learning is trying to do mathematics with singular data points, and those data points, you probably know just from regular computers. You know what a motherboard is, right? If you smash your computer open, you've got that green board with all the little silver speckles, which are switches, just like the switch on the wall over there, turning the light on and off. So the power either goes through or it doesn't. It's on or off. A qubit is different. It has got on and off, if you imagine it like a sphere, top and the bottom, on and off, but you've all got all the other little points on the ball. But you've also got amplitude and you've got phase. Now, you've got something in this qubit called superposition, right? So it is the possibility of being on and off in like sort of a probability. So just say it's 70% off and 30% on, right? The amplitude, we don't know what it is. The superposition means it's all the possibilities at once. And then when the quantum machine runs, it will collapse into either on or off, but we will never know if it was 70% on or 30% off, right? But it has got these amplitudes that decide that. And then there's another thing it's got called a phase, which is how it reacts with all the other data points. But remember, these data points are fused, and then you get this thing called entanglement. And then you've got the Hilbert space slicing through them. Now, that's very technical, I appreciate that, but you can see, because we have these possibilities of entanglement and superposition, we can do things that the classical machine cannot, right? We're dealing with a contraption that does things that a classical machine cannot. Now, these qubits, these qubits, the more you have of them, the more noise in the machine, because we're in the early days of materials engineering. So the fewer you've got in the circuit, right? The shallower your circuit is, the clearer the result. The bigger it gets, the more noise, right? Which means that you're going to have interference in your results. So at the moment, these are very experimental, but you will start to see, I'm not going to say necessarily faster results, but you'll see different results because of the different way that the problem's been approached. So for the people that are interested, these are the things that my 5 projects are sort of making clear as we look at how they work. So the classical data points get encoded into qubits, right? The circuit design, how you design the circuit, I've just told you, if it's shallow or if it's larger, you're going to be dealing with more noise in your results. The kernel is the thing where I said the 2D becomes 3D and we slice through the middle. This is put very simply, but just for the sake of this conversation. Hybrid optimization and hardware awareness we will get to as we get to the specific projects. Okay, so case study 1. Limit order books. Is it going to go up or is it going to go down on the stock market? This project is one where we're dealing with a more enhanced variance in the Hilbert space. So, for example, if you take in regular machine learning historical data from the past, so you've got in the market, you've also got something called a queue. I'm not a financial professional, but you have a queue on the stock market as well, and you don't know where you are in the queue, right? So the things you don't know, things you do know. But if we use historical data, what you do is you machine learn stuff from the past, and then you can try and use it to predict what's coming in the future. Now, in the Hilbert space, because you've got this multi-dimensional, you're cutting through a bigger space to find things that the classical machine can't. There's more variance, and you might find what we call a tail event. So something that might cause a disaster, the classical machine might not find because it hasn't got such a bigger space to check all the different possibilities, right? And I ran this on IBM Kingston. Oops, I'm really not good at this. So how do we understand this? This is probably a topic for a whole other session, but I don't suppose anyone knows what PCA is in machine learning, principal component analysis. Oh, fantastic, we've got at least one person that knows. So when you are trying to make a prediction on something where you've got lots and lots, what could we say, features, different features, you can't visualize that in 2D, right? So what you might do is run a process through all of them to try and get the closest thing of variance for them. And then so just say you had 8, then you squash them all down, and then you get 2 principal components out of the 8, which has got sort of a spread of the variance represented in the 8 features. And then you have the 2 components, and then you've just got 2 of them that you're using, right? Now, the problem is if you do that, you're flattening out the things that you're trying to find with that Hilbert space. So it's pointless. And what you're looking at here is the F1 score. So obviously this is a classical machine. This is where we are now. We're still struggling a bit at the moment, but look at the difference in the F1 score. See, it's got a bigger space to look for things in. So you see these graphs and you think, well, the blue one's bigger here, but it's not about that. It's about the possibilities in the differences between things as well. See? Okay, study number 2. Right, the A23, is anyone an iceberg watcher or a fan of watching these, the climate change and watching these big sheets of ice come off and break into little ones, and they follow them with the satellites? So this is part of a bigger project that I'm working on actually with NASA Power, but I'm using Giovanni data for this one. But this is the crazy idea, and I'm going to tell you now because the next 2 projects are coming up. There's one for a UAV and one for computer vision, and they're all joined up. So the idea is there are these things called growlers. They're small icebergs. We all know the Titanic, right? So it's like you see the tip of it, but underneath it's big under the water, and it scrapes the boats, right? And they're very dangerous. But the other thing is you might have debris floating in the sea. You might have a boat in distress. But the satellites can only see so far. They don't pick up the smaller ones. But if we could have a 24-hour unmanned plane powered by solar light in the Arctic, because it will be light nearly 24 hours, we could actually have pictures taken from 40 to 60,000 feet, which will pick up things that the satellites won't. So the whole point is, if we have the plane that flies optimized with quantum, we have computer vision running as an edge device, quantum involved in that. And then we could actually, when we've spotted these icebergs with computer vision, predict where they're going to float in the next number of hours before they hit anything, so people can get out of the way of them. That's kind of what we're trying to work on. Don't know if it will work, but it's an idea. But what's more exciting is particularly what NASA are interested in. If it does work, where can that tech go beyond the iceberg scenario? Geo-rectification of the moon is something that hasn't been thought about, Google Maps for the moon. But if you've got something that works, you can move from there. So there's that side to it too. So essentially, we've got all the time series data for, all the things making things float in the sea. And once again, a bit like the limit order book data, we are picking the features, hand-picking them, putting them into the Hilbert space, and finding the variance. And we're finding things that the classical machines possibly might not pick up. And if I've run this one as well. So looking here, now this is a simulation. When I did run it, I didn't have as much data, so the black thing was further over and the color ones are over here, but I've sort of stretched it out for the sake of this presentation. You can see for the A23A, where we do actually know the results, we do know where it ended up, this vortex, this sort of spiraling of this chaotic dynamics of the ocean. The real one is the black one. The blue one you can see is the classical prediction of that black one, but you can see the red one has actually found things that the blue one has not, once again, right? So it's not necessarily about being better, it's about finding things that might be a one-off. There's that side to it. Okay, how am I going for time? Okay, just got to optimize my time. Okay, so the next part of this, I'm going to show you the UAV that would be taking the images that would then be, you know, we would be predicting the trajectory of the icebergs picked up in the images by this plane. So power are dealing with irradiance data. So, you know, data for, you know, solar power, if you like. There are 9 kinds of it, right? It's not just sun going down. There's sun coming from the side, there's sun coming this way, sun coming off clouds. You know, when there's cloud, it's bouncing off the clouds as well. So there's lots of ways that we can obtain power from the sun. So they have an entire project based on solar powering. But there's also things like humidity and temperature. There's other things that go with that. Because if things are correlated, one goes up, the other goes up, we've got to consider those things as well. So this is, oh yes, this is the moving one. This is just showing you in red all the different places. I mean, I guess this is essentially NASA power showing you the user location, the request and the data location. It's just an animation there, it's quite fun. And some specs there for you. And the other thing I've got to tell you is I'll be presenting, fingers crossed, when we've done all the experiments and hopefully they work. In September, I'll present at the NASA Power GLOCO Summit to this project, which hopefully I'll have run in Qiskit on IBM Kingston. So we're still working at it, but hopefully it will be in September. Okay, so back to this UAV. So what is the problem with our plane? So when you fly, you can either fly above the cloud, where you can't take pictures, obviously, unless you've got radar, and that's really heavy and power hungry, so it's not really an option, even though it can be done, but probably not on a 24-hour unmanned flight. Or we go under the cloud, where we can take pictures. Problem is, you're then dealing with weather, right? You've got to keep the plane in the sky. And of course, if it runs into bad weather, it's going to be using all its energy, but it also needs its energy to fly, but also to run this computer vision contraption, right? Right, imagine, I'm trying to think of, when we did this at Cranfield, we did a small baby version at Cranfield University, and we used a Raspberry Pi, just with a Pi camera, right, to try and test this idea. But basically, in the environment where this plane would be flying, where there is like nearly 24 hours, there's these problems with the weather. You get black swan events or tail events. So sometimes if the cloud and the humidity and the temperature are in just the right combination, you get ice all over the wings and affecting those solar panels. So not only is it really taxing trying to fly in this weather, suddenly it's getting less power. But that may not be picked up by a classical machine, you see, because that is a rare event, but it does happen. And then your plane could crash, and that could be a multi-million-dollar plane, right? So we have these, just going to move on here. We have this GP kit here. So this is geometric programming. And basically this here is, you know, pen and paper. These are all the constraints on the plane, automated with this, which is in Python. And if we feed this, what we can learn from the quantum machine, I was just talking about those tail events, we can make the plane so it is foolproof according to years and years of historical data to make sure that in that black swan event, we are covered and it will be able to survive, see? And as you can see, we had some interesting insights here. It actually turned out with the classical one, the wings weren't big enough to deal with the black swan event. You needed them a bit bigger. But actually, when you look at the energy energizing the plane, you know, with its structure, actually, you could afford to make it a bit lighter. It was overkill on the classical one. So it's interesting to an engineer, you know, 16% doesn't sound much, but when you're spending a lot of money building something and you've got risk, imagine if it was something like cancer, right? Something critical, that percent is huge, right? So to an engineer, that is actually huge, 16%. I think I put, I might just because we're short on time, I had some numbers down there. But just to point out, you know, when you consider the overall picture, you're also considering safety as well as cost, right? There's a couple of things that go into it. And what I had to find during these 5 projects what I did, my friend Kustab's down at the front, at King's last summer, we ran these classically. And then what we did is we sort of sold the whole concept to talk to specialists about doing this in reality. And then I went and tried to do the quantum one to see if it was worth trying to see if we would get a result, not necessarily as better, but different, a different approach. So this is the computer vision one. So once again, we're trying to deal with tiny specks like this, and then we've got noise. So waves, shine on the ocean, tidal, you know, there's all this action happening in the sea. So we don't have enough images from 40 to 60,000 feet, right? We've got satellite images, but that's not the right distance, and we can use them. But really, what we're going to do is we're going to make synthetic data, and it wouldn't be in the form of pictures. So what you could actually do is pull all those pictures apart into numbers, if I'm making sense here, and then from those columns of numbers, you make the synthetic data as other forms of numbers of all little variants of what those few pieces of data that you have, right? And then you can learn from those. And once again, in a Hilbert space, you are picking up the difference between, you know, is it an iceberg or is it a boat? You might have a situation where it's so precise, but the quantum machine might pick it up because it's come across that in those artificial numbers. Am I making sense here? Because I'm aware this is a very technical conversation. If I could have had a half day, I would have gone into a bit more detail with some diagrams. Okay. So, oh yes, and I should point out this. This is a graphic that Qiskit will print out. It's you're looking at the glowing dots, basically. So what happens is, the limit order book is probably a better one to explain it with. You've got pairwise similarities, right? So you've learned from all the past data, and then you're putting in a new piece to try and predict how will this one do from all this information from the past. It will try and see how similar they are, right? Now you've got to be aware with a quantum machine, you're not got individual data anymore. You've got them all fused together, and you're talking about phases, right? Phases. And when the signal is strong, because you're dealing with signals, perfect. Obviously, it's different to when there's no signal at all, because as I said, on and off, or with a probability. So the quantum machine, actually, it comes out with a 0 or a 1, and you don't know what the probability was. But if you do it 1,000 times, and out of that 1,000, 700 came in as 0, and 300 came as 1, you know it's 70-30, right? That's kind of how it works. So you're dealing with signals with a quantum machine. All right, last one, I have to speed through this. This is a bit of fun. So this is a combinatorial problem. So best way to describe it, if you're a computer and you're trying to get through a maze, typically the computer goes every possible way, oh, dead end, comes back, and it tries all the different ways until it finds the answer. Now what a quantum machine does, it's got tunneling. So once again, if it's all fused together and dealing with waves, it doesn't have to do all that individual going in and out of paths, right? So what I've tried to do here, I don't know if you know what a photo mosaic is. It's where you make one big, massive image out of smaller ones, but we're taking it a step further. We're taking tweets, or X's, I don't know what we call them now. So we've got the comment as well, the country, and then we're using clip and also YOLO, which are existing computer vision tools. And they analyze the picture for facial expression like happiness, sadness, and also the items in the image. And then we take all that information and also color, and then we try and find not only something that forms a bigger picture, but so when you look through it, it all makes sense and all the same sorts of pictures with the same sentiment. So if you've got like something really evil, like someone's murdered someone, and then it's next to like someone celebrating they've won a race, you know, those kind of sentiments, they're not going to be next to each other in this mosaic. You have all the sort of dangerous ones, you know, the failures, the illnesses, and then you've got all like the happiness, all this, and it makes it interesting if you're going through, if you're clicking in and the picture comes out, it makes it better organized, right? So that's an optimization problem. Okay, so I'm just coming to the end here. Yes, so down here I was just showing the data that's gone in, so that's what we would be encoding, right? And I'm running out of time here, but what I was talking about, the energy landscape. So the more cluttered your mosaic is, the more things are disjointed and overlapping, that's high energy, and the smoother it is low energy. So the quantum machine is better at dealing with things where you've got high energy because it can tunnel through. That deserves a longer explanation, but I'm running out of time. Okay. Now, just to put things in perspective. So classical machines are better to a point because we're not speeding up what a classical machine does, you know, but like a tape recorder playing individual cassettes. What we're doing is we are using it all fused together and we're taking advantage of the Hilbert space. So really, it gets to a point where quantum will get, you know, be able to take advantage of that scenario. But actually, for what we're using computers right now, you know, using Microsoft Word and video gaming and that, you know, classical machines, that's what they're for. Quantum machines are like a GPU, a really big GPU. It's heavy lifting, right? It's for going through data in the right setup to find things and to find them quickly. That's really what it's about. Okay, and then I tried to sort of put it simply. So if you've got a guy that's dealing with data, this is what's useful. Is the data too deep or too noisy? You want your quantum kernel. That's the one where I said you go 2D, you put the line, you make it 3D, you slice through the middle. Think like that. The physics check. Is it chaotic like the mosaic, right? Is it got too many things overlapping? Well, it's really hard to put all the themes and the speech and the colors and the sports all together. We're going to use a regression. And then the scaling check. Are there too many combinations? Quantum annealing, all right? So, I mean, that's put very simply, but that's kind of like a framework that I'm going with as I do these experiments. And then I tried to kind of put them into perspective for you. So these were the things that were apparent in my experiments. And I put some images there. There's your combinatorial scaling, your representational drift, your nonlinear atmospheric complexity. Those are kind of the technical terms for what I've been talking about today. And then this is how it looks on IBM Quantum. So you send it off and then it runs. You might wait in a queue for 5 hours, but actually the experiment might only take 2 minutes. But it runs very simply. As a student, I get some free minutes, but it's perfect for my experiments. And I think if you make an account, you get some free minutes to trial as well. And then this is my, oh yes, so this is in September if I do present at the NASA GLOCO. But this one here, I am needing, I think we've got about 10 to 15 places still. It doesn't cost anything, free lunch. It's at King's at Bush House, fantastic venue. If you have a if you have a regular classical machine learning engineer or a Python programmer, someone at your workplace that is interested just to see what a quantum algorithm looks like in comparison to a classical one, because I'm going to show them both next to each other, right? We're going to pull it apart. They don't need to be an amazing coder, but they do need to kind of understand what they're looking at because it is in Python code. And I will spend the day pulling it apart. Please see either Jorge or Frank or myself. We would love for them to join us. We've never done this before. Kings have never done it before. And we just want to see what happens. And I will validate the whole thing with the Qiskit Machine Learning Digital Badge. And I can tell you that I've tried lots of programs. That one is it's dense, a lot of information, but it is by far the best one with the best visuals. So yeah, thank you for listening. I hope this evolves into something better, and I hope I can present for you when I've got some more results.
So much. Am I on? I'm going. Thank you so much. Wow, my brain's spinning. I don't know about yours. Crikey, that was fantastic. Thank you so much for that. We've arrived at that favorite time of day, lunch. So, oh, have we? Oh, okay. That's not on my one then. See, all good plans never survive contact with the enemy, right? So I do apologize. That wasn't on my one. We have one more before lunch. 15 minutes. Andy, sorry about that. Oh, in fact, you've got,
I think, can you hear me? All right, working? I can see some nodding heads, so that's great. Is there a clicker, by the way? Sorry. Thank you. Right. Cool. So here's me. So who am I? I'm a customer success engineer. I've worked with IBM for a number of years now. My specialism is in data security. So that's all things from database protection all the way through to, as we're moving into the post-quantum kind of world, the quantum safe element as well. So I work with a subset of our clients, just kind of advising, working with them, letting them know sort of what we can do and how we can help. So I'm here to talk to you today about addressing the quantum threat. So we're all familiar. I've seen quantum safe. Quantum has come up already. So what does that mean for modern cryptography? So we've got two missions, just very briefly. So we've got two missions here at IBM. So bring useful quantum computing to the world and make the world quantum safe. I'm here to talk about the second one today. So you will hear about the first. If you haven't already, you'll hear about that this afternoon, but we're talking about quantum safe here. So I want to do a bit of a level set. So what is cryptography? Cryptography is everywhere. Right? You've got about a dozen examples here of where cryptography exists today. Anywhere you've got data, you've got cryptography. So cryptography essentially is the encryption side of things. So we encrypt all of our data using the cryptographic standards, which keep our data safe in the event of a breach. Now, we can see on the screen there, we've got a list. We've got RSA, DSA, ECC, and a few others there. These are on here specifically because while today, the math required to break this level of encryption will take a very long time. So by the time it ever got breached, ever got decrypted, it would be meaningless. It would be useless to anybody. With quantum computing, that changes slightly, changes quite considerably. We're talking from hundreds of years, thousands of years, down to a number of hours. So this is what we're looking at here. So any data that we've got privileged information, we've got proprietary information. It could, if we don't take action, it could become vulnerable. So what do I mean when I say it could become vulnerable? Now, the big one that we talk about is harvest now, decrypt later. So what that means is bad guys, bad actors, they're out there today and they're harvesting confidential data. So personal information, business information, proprietary algorithms, that they're grabbing whatever they can because they know that in a number of years, be that 5 years, 15 years, they're going to be able to decrypt that data at some point in the near future if we're using one of these vulnerable algorithms. So that's a big part of it, and I'm sure harvest now, decrypt later is a term. I know it's gaining traction a lot. You know, a lot of people are talking about it. A lot of people have heard about it. But the other things that can become an issue as well once this technology, once the algorithms are broken, is it will be possible to disrupt businesses by using fraudulent authentication, manipulating digitally signed contracts, and so on. So there is big implications here. So just to take a moment to talk about the work that IBM is doing in this space. So we've worked with NIST, so the National Institute for Standards and Technology, the US organization, and we, working together with them and others, we have helped to co-create 3 out of the 4 post-quantum safe algorithms that NIST have approved. So we've got thought leaders in this space, we've got researchers in this space doing some fantastic work there to ensure that while we're bringing quantum computing to the world, we're also making sure that it doesn't break organizations and the way that we protect data today. So I talked about NIST, and one important thing to talk about here is we're expecting NIST to deprecate the first set of quantum vulnerable algorithms by 2030, and these could be disallowed by 2035. So when I talk about quantum vulnerable algorithms, it's the algorithms I showed earlier, RSA and so on. And NIST, although they're a US organization, the EU, the US, the UK, you know, we all take recommendations that NIST make. So you can see there has been a lot of guidance from governing bodies around prepare for your quantum safe migration, prepare for that journey. The messaging, as years go by, as quantum advances, that messaging is going to become more and more, it's going to be more and more strongly suggested there will be deadlines at some stage in the future. The key challenge with this, and I've touched on quantum threats already, so I won't rehash over that. I know we're all eager for lunch, I'm sure, but lack of visibility. 45% of organizations say they have full visibility into their cryptographic estate. Having spoken to a number of clients, I know that some of this is spreadsheets that relies on manual people entering the data, keeping that data up to date. If you've got 10,000 cryptographic assets, you can almost guarantee there's at least one or two things that have been missed there that are maybe out of date. We've also got lifecycle complexity. The lifespan of a TLS certificate is set to reduce down to 47 days. So we're going to have to renew our certificates eight and a half times more frequently. Now, certificate renewal is already a challenge for a lot of organizations. I believe it's 2029 when the timeframe changes. It's going to cause a significant extra workload alongside the quantum safe and everything else that we've got going on at the same time. And of course, tool sprawl. The more tools you use, the more gaps you create. Things could get lost in the mire, so to speak. And that brings me to the final slide for today. So this is our kind of 4-stage journey. This is our kind of recommendation. So stage 1 to become quantum safe is discover and create an inventory. So when we talk about an inventory, you may have heard the term CBOM, cryptographic bill of materials. So this is essentially a list of all of your cryptographic assets throughout your entire estate. So it could be in your code base, it could be in your network layer, it could be everywhere in between, your API keys, your certificates, and so forth. So once you've got that cryptographic bill of materials, that CBOM, that's where we move on to stage 2, so assess and comply. In this stage, we've got a list. Let's say we've got 10,000 cryptographic assets that we need to look at and we need to identify. Some of those will be protecting really sensitive data. Some of those won't be. So this is where we need to look through and we need to prioritize what do we need to fix? Where's my sensitive data? What cryptographic assets is that hidden behind? So we build up that prioritization list essentially. And of course, as you can see at the bottom there, audit ready reports. We all understand the need for being audit ready. So that's where this comes in. Stage 3, manage lifecycle. That's where we centralize the operations into a singular tool, where we automate and we create rules. Now it's policies and rules that are the most important thing here. Cryptography changes every day. We roll out new cryptographic keys, we renew certificates, everything changes on a frequent basis. If we're relying on the fact that, okay, we've done it, I don't need to worry about it anymore, we're opening ourselves up to a new issue next week, next month, next year. So that's where the life cycle comes into it. And then, of course, protect and adapt. Everything is changing at a very fast pace when it comes to quantum. This, like I said a moment ago, this isn't a one and done type situation. This is the first time we've ever really had to build up a cryptographic bill of materials, and we've really needed to understand our cryptographic exposure. But as we move forward, it's going to become more and more frequent. The question is going to be asked, what cryptographic keys have you got? What algorithms are you using to protect all of your sensitive data? How are you ensuring that this sensitive data isn't at risk of being breached? And I think if there was one thing that I would ask you to kind of think about from everything that I've talked about today, it's if we go, I'm not sure how to go back, so I'm not going to go back, but if we look at the RSA encryption keys, how many RSA encryption keys are you using in your estate today? Can anybody answer that question? If they can't, how big is the task that you're going to have to come up to? How long is it going to take you? How many different teams do you need to involve? Is it going to be a 2-month job? I can almost certainly say it's not. It's going to be a multi-year project. So that would be the biggest thing that I would sort of highlight is where are my keys and how big is the task? Now, Jorge has just held up a sign saying 5 minutes, and with that, I'm actually done. So I'm going to let everybody go for lunch. I hope that has all made sense, and I hope everybody sort of understands the threat that we're facing there with quantum computing. So thank you very much. I'm handing back over.
Yeah, that's brilliant. Thank you.
Thank you.
The confusion. Sorry about the confusion there. That was a cock up on our side. So now you can go to lunch. We're just going to cut lunch short a little bit, 45 minutes if we can, just so we don't keep cutting the speakers short, because obviously they've given a great deal of their time to come along and share their knowledge and experience. So if we could take 45 minutes and come back for 1:30, that would be fantastic. Thanks ever so much, guys. Thank you.